Okay, through careful observations and measurements, scientists were able to discover that magnetic field, the strength of the magnetic field, which we use the capital letter B to signify, is proportional to how much charge is moving, how fast that charge is moving, and dependent on the direction relative to that velocity where you're measuring the field. And I'll explain that. That's the most complicated part, and I'll explain that in a second. But it also, like electric field, it gets small very quick with distance from where the charge is. Okay? And the effect is quite small. The constant out front is mu naught over 4 pi, and mu naught is 4 pi times 10 to the negative 7. So this whole constant out here is effectively 10 to the negative 7. So it's a pretty small effect. Magnetic fields require special materials, very fast moving charges, or lots of charges moving in order to have a sizable magnetic field. Okay, so we're going to try and digest this and see what this means. Now, this V cross R hat is the most complicated part. Okay, so suppose a particle, here's a particle, and it's moving with this velocity. Okay. Now, what the R hat means is if I'm going to measure the field right here, well, R hat points in this direction. Okay. And so the hat, the distance is here. This is, if that's 1 meter, then this is 1 meter squared. But this is just the direction. This just means down. Okay. So when I think of this V cross R hat, remembering that cross products give us the sine of theta. So I can rewrite this in magnitude, or at least without the direction involved, as QV sine of the angle between B and R hat. So this would be the theta, which in this case is 90 degrees, divided by the R squared. So when things are perpendicular, meaning when you measure at positions that are perpendicular to the velocity, then you're going to maximize the magnetic field of this moving charge. Okay. But if it's not perpendicular, if this is your velocity, and that is your R, that's your R, that's your velocity, then you're going to get a very small magnetic field. Okay? So let's draw one example to see how that angle comes into play. To hold everything else constant, suppose I have a charge here, moving the speed v, this is my charge, and I consider a circle of equal distance centered, so a circle that is centered on this charge. So at all points along the circle, R is the same value. So that means this number is the same no matter where I am. The charge is the same for all calculations, V is the same. So all of this stuff here is the same. So all I'm considering is how does the angle matter in terms of affecting the size of the field. So if you think about straight ahead, well, R points from this where the charge is to where we're measuring the field, and that's in this direction. So V and R are in the same direction. Well, what's the sine of 0? Because the angle between them is 0. What's sine of 0? That's 0. So I'm going to get B equals 0 here. Okay, well, what about right behind the charge? What if I measure the field right there? Okay, well, now R is pointing backwards or to the left. V is pointing to the right. They're opposite each other, or the angle between them is 180 degrees. Well, sine of 180 degrees is also 0, so I get 0 here. Kind of like what I emphasized here, if I look at a position perpendicular to it, then the field there is going to be maximized. Okay, so I'm going to write max, okay, assuming a fixed distance R. Because obviously if we make R small, it'll get bigger, but we're assuming a fixed distance R. And if I go up here at top, then I get max as well. Now the directions will be different at those two places, and we'll focus on the direction of the field in a minute. I'm just trying to focus on magnitude. Okay, so we find that it's 0 in front and 0 behind the motion, and then it's maximum to the sides, directly to the sides, which means it gets bigger this way and this way, and then it gets smaller this way. Okay. So if I were to measure the magnetic field everywhere around this moving charge in this picture, then the field would be 0. It'd get bigger until maximum here. It gets smaller till 0. Get bigger till maximum here. It gets smaller till 0 again. Okay. So that's how this sine of theta comes into play. A big thing to conclude from it is that magnetic fields seem to always be going swirling around this, and they're never in front or behind it. There's never fields along the direction of the moving charge. And we'll see that's true for currents as well, because current is just moving charge. So there's no fields along the motion of the charge. Okay, now we need to figure out direction. We've kind of figured out magnitude. Again, it could change with different distances, but I think we're comfortable with that one, given that it's the same as for a Coulomb force or a gravitational force also. Okay, so one thing about this is the direction depends on this cross product, and the magnitude was just sine of theta, but the direction is given by the right-hand rule. Okay, so to play with that, we're going to draw a velocity here. Here's my charge. Okay, let's suppose I'm measuring the field right here. So that means R points here. And I want to emphasize this is where we're measuring the field created by the charge that's located here. It's not like there's a charge here, and it's not like I'm measuring the field here. This creates a field here. Okay, so my question is, what is the direction of that field? If this is the velocity and this is the R, what is the direction of the field at that location? Okay, by our right-hand rule, what we can do, we have multiple ways of doing this. Okay, we have one where you hold your hand kind of like this, where the 3 fingers form right angles. Okay, I know it's kind of blown up there, but you hold your hand like this, and then this. Well, you have to use your right hand. Don't use your left hand. It's the right-hand rule. The way you use it is that these 3 fingers are cyclical. Okay. So in a cross product, we have A cross B equals C. So we're reviewing. We've done this in a mechanics class for torque, and we're reviewing. If I choose this finger to be A, then I choose this finger to be B, and this finger will be the result. And they go in this circle this way. Okay. Now I could choose this finger to be A. That forces this finger to be B, and then this finger will be C. Or I can choose this finger to be A, which forces this finger to be B, and this finger to be C. The text likes to use this one to be A in the computations. I like to use this one. It seems easier to use this one, so I will use this one. But just note, you can use any of them, but you just have to stay in this order of A cross B equals C. Okay, so I'm going to use this one as the first vector, this one as my second vector, and my thumb is the resulting vector. Okay, so that would be A, B, and C. Okay, so in doing that, I have A pointing this way because it's V cross R hat. So V is my first vector, or A, and R hat is my second vector, or B, and the B field direction would be given by C, so that's my thumb. So this is my thumb, this is my pointer finger, and this is my other finger. Okay, so I take my finger, and I point it in that direction in B, and then I need to rotate my wrist so that this finger that I'm wiggling is pointing in the direction of R, which to do that means I have to rotate around. So now B is that way, R is that way, and you can't see my thumb, but it's below. It's pointing into the page. Okay, so that's how I use my right-hand rule. Okay, so that means at that point right here, B is into the page, and we draw that with an X in a circle. That represents the tail feathers of an arrow flying away from you. Okay, or we can just write into, and sometimes we just put an X there. Okay, so all of these are synonymous with into the page. All right, now what about up here? What is the direction of the B field up there? Well, if we try it again, we go V is this way, V is this way. Okay, now R is pointing upwards along the page. Sorry, I'm trying to get my, looking at a video. This is awkward. I'm looking at the screen while trying to move my hand so it's clear. Okay, so V is that way. R is pointing up the page, okay, which means my thumb is pointing out at you. Okay, and so that means the B field is out, which we draw a circle with a dot in the middle, or we can say out, or we just draw a dot. Okay, all those are synonymous for out. You can do any one of those. Okay, and if we did it anywhere else, we'd get this kind of swirly field. It's coming out, coming down, going in, going up, coming out. It's a swirly field that goes around this. Okay, and magnetic fields are characteristic in that they're swirly. They're swirling around the motion of the charges. Okay, so in this case, this is the same scenario. So down here, since the charge is moving that way, the magnetic field would be into the page here and out of the page here. Okay. Now up here in front of the charge, towards you of the charge, so a few centimeters above the page, the field would be pointing downward, okay, because it's about ready to curl down into it. All right. Okay, so with that, let's try just another one. Before I close out this video, I want to try another one with the right hand rule. Let's assume that the particle, here's my charge, and its velocity is out at you. Okay? So here's my dot inside the circle. So this is a charge, but it's moving out at you. So it's about to hit you. Okay? So it's moving out at you. All right. Now, what is the direction of the magnetic field right here? So the R hat is pointing that way. And I want to know the direction of the magnetic field right there. So I'm going to do my right hand rule. This one's a little awkward on my camera here. I'm going to point, that's, if I were you, it'd be a little, I'm sorry, this looks a little intimidating or something. I'm about to pick your nose. So I'm pointing my finger up at you. And then R hat is pointing up, up the page. And so my thumb is forced to point to the left. So at this location, the B field is pointing to the left. Now, if I do it over here, I'd get down for the B field, and if I do it over here, I'd get to the left, or to the right. If I do it get here, I'd get up. And this is similar to what we saw in a previous video, is no matter where we go, we see these circling fields. Right there would be that way, that way, that way, that way. So we get this circling fields all the way around this velocity that's moving up. And we can use our right-hand rule instead to get those directions. Sometimes this is easier than this, and sometimes this is easier than this. Kind of just depends on the problem. Okay, one last thing before we move on, just a little quick check, is this depends on the size of the charge, but also the sign of the charge. And so if this is a negative charge moving, well, guess what happens? Everything you just said gets reversed. The magnitudes are all the same, but now our circling is this way. Our what was in is now out. What was out is now in, and so on and so forth. Okay. The size doesn't change, but it's just the directions all change if we have a negative charge. So just be careful there. I like to do it. Everything, figure out directions as if it's a positive charge, and then if they say, oh, it's a negative charge, just flip whatever my answer was.